Well, thanks for wearing me. I appreciate that.
I know. I'm kind of appreciable guy.
Accurate.
Mm-hmm. Accurate. Shall we go ahead and take the chapter 4 and 5 quiz?
Yeah.
Sure.
All right.
Get that sucker out of the way.
Let's get that sucker out of the way.
Okay.
Do it.
Let me open her up. All right. Should be available to you on Blackboard. I'll be here if you have any questions. I'm going to give you guys my motor theory spiel. We'll see how far we get with that today. Did you guys cover motor theory very much downstairs in the intro classes?
Not a lot. Not really.
Okay, well, I'm going to go over the basic principles with you. I think you guys have somewhat of a grasp of motor theory already, and at least power generation. It's the exact same thing. It's just one, you're using energy. With power generation, you're using mechanical energy to create voltage and current, and with motors you're using voltage and current to create mechanical energy. Works the exact same principle, it's just backwards. So I put some stuff on Blackboard under course content for you guys to look at. You don't have to look at it now. I'm going to go over it with you when I share my screen here. Let me do this. Can you guys see the screen and see me?
Yeah.
Yep.
Okay, this is going to be, I don't know if you can expand me too, but I'm going to show you a little bit of stuff physically, and then I'm going to draw some stuff up on this page. So I'm going to go into this folder that says motor theory, and there's two hand rules. You familiar with these?
Yes.
Okay, well, first let's talk about the one on the left. That's the right hand rule. And what it says is that if I have a wire and I put current through that wire, now let's just say that it's direct current right now. So there's wire in that picture going in one direction, and I'm going to hold this piece of wire up vertically. What it says is that my right hand, if I put my thumb in the direction of current flow, so if there's a battery hooked to this thing and I'm going from positive to negative, we'll use standard current electron flow theory, but positive to negative from the bottom to the top, and I put my thumb in the direction of current, my fingers, as I wrap them around that wire, is the direction of magnetic flux around that wire. So anytime you have current, you have magnetism, anytime. So I'm not going to get into magnetic lines of flux, but maybe I will later. So that's the first rule. That's the right-hand rule. So the direction of magnetic flux around this thing goes in this direction where my fingers are, if my thumb is pointing in the direction of current. So real quick, if you can imagine alternating current, that goes back and forth, right? So how many times a second? How many hertz do you get out of your outlet when you plug something in?
60.
60 times a second. So if you think about this, and this will come into play later, this magnetic field is switching directions 60 times a second. So it's going like this, and then it's going like that, and it's going like this, 60 times a second. So you guys ever heard of transformer humming?
Yes.
You know why it hums?
Because of the 0 degree line.
Because it doesn't know any words.
Ah, ha, ha, dad jokes. That's great.
Got him.
Yeah. I have to throw that in there because it's a really bad joke, but I think it's funny. But it's actually something, I looked it up. It's called magnetostriction, I think is a term for it. All it is you're hearing that magnetic field going in and out 60 times a second around all those windings, all those coils. So kind of cool. But anyway, all right, the left-hand rule. The left-hand rule says that if I put my, I'm going to use the same piece of wire. If I have a loop of this thing, so I got both ends right in front of my face, and let's pretend that, I'm going to try to face the camera better here. Let's pretend that my right shoulder, does this look like right to you, or does it look like left? I think it's mirrored.
It's right.
That's right. Okay, so my right shoulder, we're going to call that positive for the sake of DC current, and this is negative. So I'm going from right to left. Let's say electrons are going to flow around this. So I'm the battery, and I'm hooked up positive over here, negative over here. Okay, so I've got somewhat of a loop here. The left-hand rule says that if I'm going, or the right left-hand rule, it's not going to work out very well going positive and negative. Let's switch that. I'm going to go positive over here, negative over here, so I can use my left hand. You'll see what I mean. But if I have my middle finger and I do one of these little doodads, and I have, it's kind of cool. I'm going to put my middle finger in the direction of current flow. Okay. B is going to be the direction of the magnetic field. F at that point is going to be the force. So if the current where I'm holding straight out is going in this direction towards my right shoulder, the magnetic field is in this direction, I'm going to get a force on this wire straight up. Okay, so that's direct current. Now keep this in mind that in a battery, I'm only going current in one direction. AC, that current's going back and forth. So if this, I'm going to try to draw this better on the screen so you can see it, but I want you to get somewhat of a real life. This is what I do in the lab when I'm doing my motor theory schmear. It's just kind of hard to do this online, but if I use that force straight up, so my direction of current is this way, it's going to want to lift the wire up like this, right? So it will start to go in this direction. If I change the direction of current, like an AC 60 times a second, it will want to go this way and then change the direction to current the other way. And I can't really do it with my thumb, but then the force on this thing is going to go straight down. So it's hard to visualize without being right there in front of you. But if I had this loop of wire, and I could show you where the direction of the magnetic field is and where the direction of the current is, you're going to get some kind of force on this thing. And that force will be dependent on how many turns there are in the wire, how big the wire is. That all determines the amount of magnetic flux you get out of this thing when you put current across it. So I'm going to try to scale this image down a little bit so I can draw on here. Oh, that's too big. this thing here. Oh, there we go. That's better. I put a YouTube video on here too. That's helpful for me to visualize this stuff better than I can just draw it on the screen. But let's say that I have a piece of wire that I'm going to draw it like bird's eye view right now. Let's say it looks like this, and I'm putting this in some kind of a loop, and I go plus, minus. So I'm going to put current through this thing in this direction. And then back. So this is current.
Okay.
If you can imagine using the left-hand rule, if I put my left hand on that thing, and you're going to have to try to visualize it yourself because I can't put my hand into the screen. But if I put my middle finger in the direction of current flow and my index finger in the direction of the magnetic field, so you have to kind of put the right hand rule of the direction of magnetic field into play here. On the left hand side, we're going to get, let me think about this, current that way. So on the left hand, this is going to want to bring the left hand side towards you. All right. And the right hand's on this side, the direction of the magnetic field is different now. Do you see that? If you wrap your finger around the left side with your thumb pointing in the direction of current, you're going to get a direction of the magnetic field that's different than the side on the right. Do you understand what I'm saying? Over here, you have a different direction of magnetic field than you have over here because the current's going in different directions, right? So that changes the left-hand rule, making the force on the right-hand side go down or away from you. So if I can draw this like three-dimensionally, I'm going to have the same plus and minus. But just imagine that this side is starting to come towards you and the right side is starting to go away from you. Does that make sense?
Yep.
Okay, so the left-hand side is coming towards your face and the right-hand side is going away from you. Now, I'm going to keep going in that direction. So all the rules still apply. But once I get to a place where both of those ends line up, so here is the left side, and let's say the right side has gone almost all the way 90 degrees from you. So here's plus, here's minus. I know my art sucks, but imagine the left side is in your face and the right side is completely away from you. So it's vertical or what do you call that? Not parallel, but perpendicular to you. All right. Once it gets to that point, it's going to want to just stop there, right? Because there's no change in current. It's just going to want to go in one direction and then stop because current's still going the same direction, right? So for a DC motor, because we have direct current, we have to put something called a commutator in there. And the commutator reverses the direction of current flow so that that coil will keep spinning. Does that make sense?
Yeah, it kind of artificially creates AC inside the motor.
Yeah, that's perfect. That's exactly what it does. So you're applying direct current, but the commutator takes the current and applies it using those brushes that actually touch the stator to reverse the direction of current flow to keep that thing spinning. So then once it gets back 180 degrees from where it started, then it reverses again and it changes the magnetism. So yeah. Do you have questions on that? Man, this is really hard to do virtually, but the point is with a DC motor, you have to have a way to change the direction of current flow. So the little motors that you have on your trainer, those are DC motors. So those have little commutators in there. Any questions on that before I talk to you about three-phase?
No.
Nope.
Okay.
How about an AC motor? Is it pretty much the same except for no commutator?
And AC, well, that's what we're going to get into.
Okay,
Oh, single phase?
Yeah, yeah.
Well, hang on to that for a second, because once you understand three-phase, the single-phase AC will make more sense.
Okay.
Okay, I'm going to scroll down to all right. So a three-phase motor and a DC motor, the windings are going to look a little bit different than an AC motor. But if you look inside a motor, it's going to look pretty confusing, like this picture down here. You can't really tell what's going on there, but if you take one set of windings, see if I can draw it. So like here's one set. And then directly opposite is the other end of that winding. So it's down here somewhere. So that's one set of windings. And then if I use a different color, you're going to have a set opposite of each other. So, and this might not be exactly right because there's so many different sets of windings in there, but that's one set. That's another set. So in an AC motor, and let's look at this three-phase schematic, the one at the bottom first. But if you think about, so here we've got a graph of current flow, okay? So this is not voltage, this is current flow. If you remember from power distribution, power creation, it's the same principle, right? We're using mechanical steam or some kind of nuclear energy to turn a shaft inside of this I guess you'd call it the turbine that spins inside the generator. There's going to be some permanent magnets, like in this picture, the GIF that's spinning up there. Inside of there is a set of magnets that's spinning around these windings. And then the amount of current that gets generated, say through winding set A, the blue one, depends on how quickly the magnetic lines of flux are being cut. And that's really going to be hard for me to show you virtually, but picture it this way. If you've got, let's say, a winding up here. So there's one winding, there's the other end of it, okay? And then I pass that magnet that's spinning by it. So I'm spinning in this direction. Because of that left-hand rule of the magnetism going around that coil, there's a certain direction there. And I'm gonna put that in a different color, but let's say the direction of magnetic flux looks like this around that coil. As that magnet approaches those, it's going to start cutting those faster. Okay, and you can't see these magnetic lines of flux. They're invisible magic stuff. But as this magnet starts to approach those lines, when it gets towards the top, closest to it, at that point, it's going to be cutting through these lines of flux faster than it was down here. Okay. On the opposite end of the spectrum, for a motor, as we apply current, let's say on this red phase A, as we apply current and it starts to reach its peak, the magnetic field pulling on that thing gets stronger and stronger till it reaches the peak, and then it switches direction and the polarity changes and it starts to push that magnet away from the winding. Does that make sense? So what you're doing with the three-phase motor is all three phases are creating a rotating magnetic field. That rotating magnetic field is what spins the shaft. And I used to have a really good animation of the rotating magnetic field, but the only other way I'll show you, and this is the easiest way for my brain. I'm gonna put, this is a, let's say a Y set of windings. Okay, so I've got all three phases here. And let's call this, let's call this the current through A, the current through B, and the current through C. So I need 3 volunteers.
Okay.
There's only 4 of you, so there should be a good chance that you're going to have to volunteer here.
Yeah.
Okay, Garrett said yeah. So this is Garrett over here.
Okay.
All right, you're phase A.
All right.
All right. Tyler's phase B.
Decent.
And who's the lucky phase C who wants to fight for it? Justin. All right, Justin's down here. These really handsome stick figures. All right, now think of it this way. Each one of you has a really big hammer. And I mean that in the cleanest way possible. Okay? The picture all of you have a really big hammer. Now, who's phase A? Garrett?
Yeah.
Picture it this way, and this is sort of how it works, but not really. So on the inside of this motor, we have a shaft that we're going to apply current to these windings. And depending on how we phase it, it's going to turn in a certain direction. And I'll come back to that in a minute. But let's say we're going clockwise, A, B, C, A, B, C, right? So every time Garrett applies current to this winding, he hits that thing with a hammer, right? And then it goes this way. Now, Garrett on the graph has just hit this thing with a hammer to keep it moving. It's going away from Garrett now. And now we're starting to approach phase B, which is Tyler. Okay, so now Tyler's getting amped up. He's getting pretty crazy with his current and his winding. And it reaches the peak of his current right here. And Tyler hits it with a hammer. Okay, then we're going away from Tyler. Tyler just hit his thing with a hammer, and it's going away from him. Now we're starting to approach Justin. Okay, then as we get to the peak of Justin's current right here, he's going to hit it with a hammer. So ABC, 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 60 times a second, you guys are pulling and pushing on this motor shaft.
Okay, that was my next question. So say on the green one where it's before it gets hit, it's ramping up, the magnetic fields are getting pulled to each other, right? And then
Yeah.
before it fluctuates, it pushes after
Right.
it changes direction. Okay.
After it changes direction, it pushes. So if you pick one point in time on this graph, and I'm going to have to clear, I'm going to do an eraser. Yeah, there's an eraser. I'm going to erase all this stuff over here. So let's pick one point in time on this graph. Let's just say right here. At this, right there. At this point, I'm going to try to highlight what's going on. So who's red? Garrett, phase A.
Yep.
So at this point, you are doing a little bit of pushing, right? Because we're below the what do you call this?
Zero line?
Yeah, there's a name for it in the AC theory class
Oh, I'm sorry.
where you switch directions.
Oh yeah. Oh, what is it?
Alternate or something. Anyway, you know what it is. I got to go back to my book to figure out what that line is called. Alternation. Alternation. That's what it is. All right. So you're a little bit below that line. So you're doing a little bit of pushing right here, right? Just a little bit.
Mhm.
Tyler is approaching his peak. So he's doing a lot of pulling right there.
Yep.
And Justin is doing just a little bit of pushing, but he's starting to approach the point where he will start pulling. Does that make sense?
Mm-hmm.
So
Yeah.
the fact that it's alternating by itself creates the rotating magnetic field all by itself. You don't need a commutator because it's reversing direction already.
Yep.
Okay, so once you understand that, you think about a single phase motor. It's the exact same thing, except you only have one phase. I'll try to draw that up. So with a single phase motor, let's say you got, there was a really good drawing of this earlier. I don't remember if they put like the permanent magnets on the inside of the motor, but let's say, this is a north pole. I'll treat it like a DC motor, and this is a south pole. No. This would also be, so like N plus and N minus. And then this would be south plus and south minus. Okay, so then as that thing is spinning, so let's say it's right here, and we're approaching the North Pole, we're going away from the South Pole. So that would be on one sine wave. Instead of having three of these things, you just have one.
Okay.
So as we're approaching the North Pole, let's call it like right here, we're also pushing away from the South Pole, if that makes any sense. But the current reverses itself automatically with alternating current, right? So you don't have to worry about that commutator. It does it automatically. The only weird thing about AC single phase motors is sometimes it needs a little help to get started. So a lot of them, bigger horsepower especially, have capacitors on there, capacitor start motors that help kickstart the process.
Mm-hmm.
That's like, I don't know if you can see this. Oh, this guy. Yeah, you can see that. So see this little, when you see a single phase motor that's got this big, looks like a growth on top of it. There's a capacitor.
Yeah.
That's a cap start motor. All right. And then this one over here is a 3-phase motor. And we're going to go over how to hook those up next. As long as you guys got your brain wrapped around the theory behind what makes these things spin. And that's really, for the sake of this class, that's all we need to know. If you guys want to get into the particulars of the different kinds of squirrel cage and all this other stuff, in my experience in the field, especially when it comes to troubleshooting, there's going to be, maybe you'll end up in a place where you're working on motors, rebuilding motors and all that. Then it's going to be important to know a little bit more. We will talk about troubleshooting motors in 151, but knowing all the different kinds and types is something that you would have to be specializing in motor building or motor repair. But it seems like you guys have a grasp on the principle, right?
Yeah.
Nick, you look tired.
No, I'm just listening, sir.
Call me sir is like putting an elevator in an outhouse.
Well, I like to.
Alone.
That's fine. I treat them both the same. So if you get in an elevator after me, you'll find out what I mean.
Do you know what movie that's from?
um,
You're probably the only one that would know.
put in,
It's probably before even our time.
it's
It's a Patrick Swayze movie.
yeah, Roadhouse.
Roadhouse, yeah.
Yeah, the guy with the white beard that rents him the
The old
apartment.
farm guy.
Yeah.
You guys
Damn,
seen
that-
Roadhouse? Garrett, you seen Roadhouse?
Nope.
Oh man.
I know who Patrick Swayze is, though. I'm doing pretty good.
Yeah, he's dead.
Nothing.
Okay. What else do we need to cover here? 3-phase 9-lead motor. So on this motor behind me, it's got a diagram on it that looks like this, but without the right-hand side. So the motor behind me is $208 480. It's got on its nameplate drawings that look like this, but they're not blank. They're filled in. So using the drawings that's on there, you're going to be able to, after we talk today, tell me whether or not they're hooked up in Y or delta. So here's what this means. Inside these motors, and you guys have had a question like this on your homework. You might have even seen it on your quiz if it popped up for you. But if you're wiring up a motor for a high voltage operation, are the windings hooked up in series or parallel for high voltage?
Should be in series.
Series. And low voltage would be parallel.
Right.
What that means, and this is the way I think about it, right? Think about a transformer. If you're going to knock 480 volts down to a more usable voltage, like let's say you got 480 coming in and you need a transformer to knock it down to 120 for your house, you're going to need more windings or more of that inductive reactance to knock that voltage down, right?
Right.
That's the way I think about it. So higher voltage operation is series because we need to knock that voltage down a little bit more. You could probably hook it up in parallel, but your motor will either burn up or spin too fast or something. But here's what this means. Inside that motor, remember, the inside of the motor doesn't look like this. It looks like that. Okay. But all these individual sets of windings are connected in such a way that they're either Y or delta. Okay. So there's obviously in that motor more than one set per phase, but this is how they're hooked up. So in the case of a Y hooked up motor for 480, which is high voltage, are we going to hook these up in series or parallel?
In series.
Series. So what that means is we're going to take, for instance, this right side. So from 2 to 5, it's actually a winding. Looks like that. And then from the middle connected point to wire number 8 is for 480 volts, what you would do is take these two and just hook them up together. That would make current flow through both of those series, right? And then same for the other side. 1 to 4 or 1 through 4 winding, you would hook up 4 to 7. So on this Y diagram, we're going to go for 480, we're going to hook those windings up in series. So 4 to 7, 5 to 8, 6 to 9. By the way, 1, 2, and 3 for all of these is where your line voltage is going to come in. So this would be L1, L2, and L3. So for high voltage Y, which is over here, and you guys are going to need to know this for homework and quizzes. High voltage Y, 4 to 7, 5 to 8, 6 to 9. So that's what the diagram on a Y motor would look like. So let's look at low voltage Y. For low voltage, we're going to take those windings and parallel them. So imagine it looks like this. You got one winding here and one winding here. And we'll call this, we'll just call that 0, 8, 5, and 2. So this represents this side of that Y set of windings. For low voltage, so let's say, and all this means is that, let's say in my garage here, all I have is 208. I don't have 480. So I need to hook this motor up for low voltage operation. So I need to parallel these windings, which means I take this whole thing and move it right next to that winding. So it would look like this. This becomes 5 and this becomes 2. And those two get connected. Does that make sense? So the bottom side then would look like this.
Yep.
0, 9. And this is what, 6 and 3.
Yeah.
So for low voltage, if I'm hooking this thing up to 208, I need to parallel these, which means I take this winding and put it right next to that one. So I'd have 6, 3. So that means these tie together and these tie together. So what does that mean on the drawing?
Means 6, 5, and 4 have to tie together?
Yes, it does.
Okay.
So on the nameplate, you're going to see something like this. So what are the connections then? I just showed you 2 of them. Right here is one.
So
Right here's another one.
yeah, you connect the dots, right? So 4, 5, and 6 would be one line. 7, 1 would be one line. 8, 2 would be one line. 9 and 3 would be one line.
Very good.
Okay.
So think about it this way too, and I'll show you on the drawing, but make it a little darker. If I'm going to parallel all these windings, 2 would go to 8, right?
Yep.
1 would go to 7. 3 would go to 9. And then 4, 5, and 6 would all tie together. So on the nameplate, what it would look like is 1 to 7, 2 to 8, 3 to 9, and then 4, 5, and 6 tie together. So the left-hand side what's on the nameplate itself is what you're going to need to know. But looking at these drawings of the Y and delta, you should be able to figure it out. So if I asked you a question of, I gave you a picture of this and said, is that low voltage delta, low voltage Y, high voltage delta, or high voltage Y? You should be able to look at these two pictures and say, oh, that's low voltage Y, right?
Right.
Okay, now let's look at the deltas. It's the same exact principle. So high voltage, what are we doing to the windings?
It's gonna be in series.
Series. So in this case right now that I'm talking about, we got 480 volts available. We need to hook it up to this motor. We're going to take these sets of windings and parallel them. So this is a winding, this is a winding, this is a winding, this is a winding, or series them. Okay, so high voltage delta, all we're doing is taking 6 to 9, 4 to 7, and 5 to 8. So high voltage delta looks like this. Everybody understand that?
Looks the same as high voltage Y.
Huh?
I said it looks the same as high voltage Y.
That was my next question. You notice that?
Yeah.
So
Yeah.
high voltage delta and high voltage Y are hooked up exactly the same. Low voltage delta is different though. So let's look at here's what I always tell people. For low voltage, are we series or parallel?
Parallel, right?
Parallel. So I have this Delta 9 lead motor, 3-phase, and I have 208 in my garage I need to hook up to this motor. That means I need to parallel these windings. What I always tell people is put this thing into 3 sets of triangles. You see the 3 triangles?
Mm-hmm. Looks like the Triforce on Zelda.
That's right. I have no idea what you're talking about, but that's right. Okay, so there's your 3 triangles. Now take those 3 triangles and stack them on top of each other. Those are your connections. So I'm going to erase those so you can see them a little better.
Does it matter in what order
Nope.
they're stacked?
All we're doing is making connections. So just take those 3 triangles and stack them on top of each other.
Okay.
So what would your connections be? 3 would hook up to which other 2? You're stacking those triangles on top of each other.
3, 1, and 2, or
Nope.
3, 1, and 5, 3, 9, and 5, right?
3, 9, and 5.
Right.
You see that? If I took those 3 triangles and stacked them on top of each other, so 3, 9, and 5. What else? 1,
1, 6, and 7.
6, and 7. So 1 to 7, and on a nameplate it looks like this. What else?
Probably the last 3.
2,
2,
8, and 4.
yeah.
So that's what a low voltage delta looks like. I'm gonna see real quick if I can find, instead of moving my camera to show you the motor nameplate behind me, but so I can show you what what I'm talking about. Okay, here's one.
But if you do that, does that mean that you have a high leg in that?
High leg, what you're talking about, like the wild leg.
Yeah, 230.
Yeah, that's in a transformer. So that's where you center tap a delta winding and it gets all funky. I rarely see, I've seen that one time in the field. Was that you that was telling me you saw it once?
Yeah, Butch's Pizza. They run a high leg transformer to their trucks when they hook them up outside.
All right, so I pulled up this picture of this motor nameplate. And let's see if we can you guys see the drawings over here on the right that say low voltage and high voltage? Oh, that's 12 lead. Crap. Hang on. No, I want to zoom out. There we go. There we go. There we go. It's not working well. If I can ever get this done, you can see what I'm getting at, right?
Yep.
So this is the kind of drawing that you would see on a motor nameplate. But if the nameplate was all scratched up and you needed to know how to hook it up, you could do it without having the drawing, right? That's the point.
Yes.
So what this is telling us is that, hey, if you're using low voltage operation, so on this motor, it's 230, 208, let's say. Let's say we're using low voltage operation. It's saying, hey, hook up 1 to 7, 2 to 8, 3 to 9. And then hook 4, 5, and 6 together. So is that Y or delta? Low voltage.
Why?
Voltage Y.
Low voltage Y. So that all that's saying is that's how those motor windings inside of that motor are hooked up. They're in a Y configuration. And you know, if that nameplate was all scratched up, you would know that you hook it up like this. Tie 4, 5, and 6 together. 1 to 7, 2 to 8, and 3 to 9.
Will they ever show a neutral tap on the motor, or is that just?
For single phase, they would, but for 3-phase, there is no neutral.
Okay.
All this middle point means, I think you're thinking about a transformer Y.
Yeah.
that middle point is your neutral in a transformer. In a motor, all it is the ends of those windings 7, 8, and 9 are hooked together internally.
Okay.
Okay. All right. And then the last thing I'm going to show you, if I can find a good picture of it. So what we'll do next time tomorrow is we'll hook up the 3-phase motor behind me using the information that we just learned. I just want to try to show you what I'm talking about. All right, this is sort of a good image, but you see this little box here? Whoops. All right, everybody unmute your microphones real quick.
Mm-hmm.
All right.
Okay, you ready? Let me tell you something. You see this little box on this motor? It's got all the wires sticking out.
Peckerhead.
Who said that?
I did.
What's it called, Nick?
Peckerhead.
Say it louder.
Peckerhead.
All right, I have to, whenever that comes up in class, I have to see who giggles. And I guess Nick is the only one.
Well, because the first time they ever sent me to get that from the electrical store, the lady working the counter was a female, and I was like, I need a peckerhead, and she's like, a peckerhead, and I was like, yeah. So she was more man than I was, turned out. So
Why is it called that?
I don't know.
because the
That's what it's
part that hooks to it, the whip, they call it in electrical terms, is called a horse cock. That's the old school way of saying it. So if you've got a horse cock, it's connected to the peckerhead. Because
Okay.
it was a big floppy piece of connection. There you go.
Okay.
So on this motor, it's got the lid on it, but this is the peckerhead on this motor, and that's a legit thing. It's what it's called, is a peckerhead. It's funny, I know, but it's legit. So the reason I'm telling you this is because tomorrow what I'm going to show you is we're going to make everything that we just learned about 9-lead connections, and I'm going to take this 3-phase motor behind me and we're going to hook it up, because if you open up that peckerhead on a motor and you know you got to hook it up, well, there's going to be 9 wires sticking out of there and you got to know what to do with them, right?
Mm-hmm.
So this is what we'll get into tomorrow, but yeah. Anybody got any questions? Is that all making sense?
So
Or
when they talk about it in terms of Y or delta, is that's the actual vectoring on the inside, like the actual winding connections, right?
Go ahead. What'd you ask? I'm sorry.
So when they talk about it in terms of Y or delta, that's the actual winding vectoring on the inside of it, right?
Yeah. Yeah.
Okay.
So if you got inside of a motor, just a second. You take the end bell off of a motor and you see this. It looks confusing, right? It just looks like a bunch of copper. But Y or delta configuration means that if you took this thing completely apart, unwound all that copper, you might have this winding is connected to that winding. You know, it's either in this configuration, it's hard to, like, it doesn't look like a Y or delta just looking at this picture, but this winding is just a copper wire wrapped around and around and around and around and around, and then there's two ends sticking out, right? So where those windings are configured at in this motor, the arrangement of them is either going to be in a Y or a delta. It all has to do with what kind of voltage you're using, what horsepower, how much torque you need, like where the magnetic field is going to be placed, right? Or where those windings need to be placed to have the correct amount of torque, that kind of stuff. I'm not an expert on the manufacturing of motors, but that's the principle behind it.
Okay.
So it's either going to be set up in a Y configuration or a delta configuration. Either way you do it, you have to know how to hook those 9 wires up, right?
All right. I mean, I've done it a bunch of times, so I can follow instructions, but understanding the principles behind it is probably that's the hardest part.
Yeah. Okay. Well, since any other questions? So now that you know that, and you guys were all taking really good notes, this under motor theory, the motor theory folder under course content, this one is a practice, and I can practice with you as many times as you want. But now that we've talked about it, there is a homework assignment. This is the only homework that you have that's due this week. I pushed the next 2 chapters off until the end of next week, if I remember right. Let me look.
Okay.
This is a really short assignment, but it's, so wait a minute, I didn't. So chapters 6 and 7, I pushed those back a week. So the only homework for this week is going to be this 9-lead 3-phase motors, and it's everything that we just talked about. So if you go to that homework assignment, it's actually down here at the bottom. I'll move it up. You got these pictures, and it asks you, okay, is this high voltage, low voltage, delta, or Y?
Okay.
And you should all know how to do that now. If you don't, it'll be on YouTube in about an hour.
Easy peasy lemon squeezy.
All right. Okay, well, that's all I'm going to jaw at you for today. I did put the next lab up on the drive. If you're ready for a new one, you want to start working on it, but I'm not going to go over it yet today. I want everybody to get caught up. And
okay.
What is the thing on the far left side of that lab?
Oh, the selector switch, lab 8.
Yeah.
That's your selector switch.
Okay. Gotcha.
So we'll talk about selector switches and limit switches next time. So that 9-lead 3-phase motor windings homework is due Thursday. Everybody got that?
Yep.
Yep.
All right. Well, that's it for today, folks.
All right.
All right.